Hello everyone. So this is our second hour of work power energy. Here we will talk about spring potential energy, work done by the spring, what is potential energy in general, what is mechanical energy conservation, few questions based on mechanical energy conservation and followed towards the end with power. So without wasting time, let's start doing the second hour of work power energy. But first thing we need to discuss is what is the work done by a spring. So as to understand what is the work done by a spring, first visualize a spring with one end of the spring fixed and the another end, which I am calling A, free to be moved. Let's say initially the spring is in its natural length. If I ask you to elongate the spring, in which direction you will apply the force on point A? So sir, we will apply force on point A towards right. By Newton's third law, when an external agent applies the force on point A towards right, what will be the direction of force applied by the spring? So sir, if the force external is towards right on the spring, then the force applied by spring will be towards left. So first thing to understand is, if we move the end A towards right, the force applied by external agent has to be towards right, while the force applied by spring will be towards left. Now I ask you, if you elongate a spring from its natural length, what will be the sign of work done by the spring? If you elongate a spring from its natural length, what will be the sign of work done by the spring, not by the external agent? So you will say, so if I move the point A towards right, the force by the spring is towards left. So the angle between force and displacement is 180 degree. So the work done by the spring has to be negative. Hence we can say, when you elongate a spring from its natural length, the work done by a spring is negative. Now let's think of another case. Again, you have the same spring, the left end is fixed, the right end A is free to move. Now I'm asking you to compress the spring. To compress the spring, you will apply a force towards left. So this will be the force external. When you apply force towards left, by Newton's third law, the spring will apply a force of equal magnitude in opposite direction. So the force applied by the spring will be towards right. Now you are compressing the spring and the spring force is towards right. If I compress the spring, the point A moves towards left while the force is towards right. What will be the sign of work done by the spring? So you will say, if we move the end A towards left, the force by the spring is towards right. So force is towards right, displacement is towards left. Again, the angle between force and displacement is 180 degree. So the work done has to be negative. So sir, can I say that the work done by the spring is always negative? Because I learned that when you compress the spring from natural length, the work done by the spring is negative. When you elongate the spring from natural length in the second part, the work done by the spring is again negative. So can I say that work done by the spring is always negative? No, that will be wrong. Why? Let's see this case. Let's say you have a stretched spring, a spring which is already elongated, which already has length more than its natural length. So if you have a stretched spring and you move the end A towards left, so sir, in case of a stretched spring, some external agent must be applying a force to keep it stretched. So the spring force will be towards left. Now, if we move the point A towards left, so as to decrease the deformation in the spring, if we move the point A towards left, so as to decrease the deformation in the spring, then beta the work done by spring will be positive. So if the end A is moved towards left, spring force is also towards left. So the work done by spring is positive. I can show you one more case where spring does positive work. Let's see. Let's say you have a compressed spring. So this is the natural length and here we have a compressed spring. So if you already have a compressed spring, it means that some external agent must be applying a force towards left. So if some external agent is applying a force towards left on this compressed spring, the spring must be applying a force towards right. Now again, if I move the point A in a compressed spring towards right, if I move a point A in a compressed spring towards right, the force by the spring and displacement will be in same direction. So if the end A is moved towards right, in the case of a compressed spring, if the end A is moved towards right, the spring force is also towards right. Hence, the work done is positive. So here we have learned 4 cases. From the natural length, when the spring is compressed, work done by spring is negative. From the natural length, when spring is elongated, the work done by spring is again negative. When you have a stretched spring and you decrease the elongation in the spring, the work done by spring is positive. If you have a compressed spring and you decrease the compression in the spring, the work done by spring is positive. So I say one simple statement that a child should understand, which is this: when the deformation in the spring increases, work done by spring is negative. So if you have a compressed spring and you compress it further, you are increasing the deformation, then the work done by spring is negative. And when the deformation in the spring decreases, for example, let's say you have a stress spring and you are decreasing the deformation, you are bringing it back to the natural length. When you decrease the deformation in the spring, then the work done by spring is positive. You will be able to answer it more quickly once we learn about the spring potential energy and what is actually the definition of potential energy. So, moving on. Formula for work done by the spring. Let's say you have this spring which has some natural length marked here, and let's say there is already an elongation x in the spring. Now let's say we increase the elongation by an infinitely small amount dx. We know that the force applied by spring will be equals to minus kx, because the force will be in direction opposite to the displacement of the end A from the natural length. So we can say force equals to minus kx, the infinitely small work done equals to minus kx dx. Why? Because the force is backward having a magnitude kx, the displacement is forward dx. So the magnitude of force is kx, the magnitude of displacement is dx, and the angle between the force and displacement is 180 degree. So we will get the infinitely small work done to be negative. So we will write dw equals to minus kx dx. Once you know dw, game over. You can find the overall work done by the spring just by integrating on both the sides. So if you integrate on both the sides, on the left hand side, integration of dw gives you the overall work done, and on the right hand side you will get minus kx dx. Limit of integration from, let's say, initial elongation x1 to final elongation x2, initial deformation x1 to final deformation x2. So we know that integration of x dx gives us what? X square by 2, and k is a constant that can be brought out of the integration. So you get work done by spring equals to minus k times x square by 2, lower limit x1, upper limit x2. Bachcho, always substitute upper limit minus lower limit. So you get minus k into x2 square minus x1 square. Now understand that what we have found here is work done by the spring. In many a question, they will ask you what is the work done by external agent. So the external agent applies force outwards kx to make an infinitely small displacement dx. So if they ask you work done by external agent, that will be k by 2 into final deformation square minus initial deformation square, while the work done by spring will be minus k by 2. Okay, so in case of external agent, you get equal and opposite amount of work. Now let's say we take the final elongation as x2 and initial deformation as x1. If bachcho, the initial deformation is 0 and the final deformation is x. If let's say initially the spring is in natural length, so you will say x1 has to be 0, initial deformation is 0, and let's say the final deformation is x, then you will say the work done by spring equals to minus k by 2 into x square. So if a spring deformed from natural length by a distance x, then the work done by spring is minus k by 2 x square, and this is used very commonly many a times. So let's move on. If the work done in stretching a spring by distance x from natural length is w, work done by who? Work done by external agent. Determine the work done in further stretching it from x to 2x. So if the work done in stretching it from natural length by distance x is w, then what is the work done in further increasing the elongation from x to 2x? So here you know that work done by spring equals to minus k by 2 into final deformation square minus initial deformation square. And the work done by external agent who is deforming the spring slowly is plus k by 2 into final deformation square minus initial deformation square. Sir, why have you taught work done by the spring, not the work done by external agent? Because in all the questions that we are going to practice later, the spring will do the work. And when students write the work done by spring, they forget this minus sign. That's why it's really important to remember the work done by the spring as minus k by 2 times final deformation square minus initial deformation square. Now, we can say that W equals to k by 2 into x square minus 0 square. As per the problem statement, when elongated from natural length by distance x, work done is W. Our mission is to find how much work has to be done to further elongate it from x to 2x. So let's say this time the work done is W dash. So you will write second equation, W dash equals to k by 2 into final deformation square 2x square minus the initial deformation square x square. Now beta 2x square minus x square gives you what? 4x square minus x square, that is equals to 3x square. So here in place of whole of this numerator, just substitute 3x square. So you will get W dash equals to k by 2 into 3x square. Now dividing the equation both the side, you will get W upon W dash. This k by 2 get cancelled. In the numerator, you will have x square. In the denominator, you will have 3x square. So you get 1 by 3. Hence, the work done in elongating from x to 2x is 3 times the work done in elongating from 0 to x. If I ask you further without raising pen, what will be the work done in elongating from 2x to 3x, and then from 3x to 4x, and then from 4x to 5x? It follows the pattern of Galileo's law of freely falling body. So here you got the work done from x to 2x as 3w, here you will get 5w, here you will get 7w, here you will get 9w. Try it out. So let's see the next example. Now here on an inclined plane we have a mass m initially at rest. Question is, if all the surfaces are frictionless, there is no friction anywhere, determine the maximum compression in the spring. So what will be the maximum compression in this spring when you release this block or ball of mass m? Since it is a frictionless surface, there will be no rolling whatsoever. So the ball will slide down straight and then will go and compress the spring. Now, all you need to think is, at the time of maximum compression, what will be the speed of ball? At the time of maximum compression, so first the ball will slide down, it will gain some speed and then it will go further and start compressing the spring. At the time of maximum compression, what will be the speed of the ball? So sir, at the time of maximum compression, the speed of the ball has to be 0. Once you know this, majority part of the question has been solved. Now all we have to apply is work energy theorem. So visualize the final case. So this is final. This is the initial case. Initially the ball is at rest, so its kinetic energy is 0. Finally again the ball is at rest, so again its kinetic energy is 0. We know that from the statement of work energy theorem, work done by all the forces equals to change in kinetic energy. Here on the ball 3 forces act. The force of gravity, yes sir, the force of normal, yes sir, and the force of spring once the ball reaches the spring. So we can say during the journey of ball, forces acting are gravity, normal and spring. Tell me, from the initial state to the final state, what will be the work done by gravity? So you will say, sir, gravity is a constant force downward. Work done by gravity will be force times displacement in the direction of force mgh. What will be the work done by normal? Sir, when one surface is fixed, the work done by normal is 0 because the force and displacement are perpendicular. And the work done by spring will be equals to, sir, the work done by spring is minus k by 2 into final deformation square minus initial deformation square. Here, initially there is no deformation in the spring, but finally we have taken a deformation x. So the work done by spring is minus k by 2 into x square minus 0 square, that becomes minus k by 2 x square. So we will write work done by all the forces equals to change in kinetic energy, work done by gravity plus work done by normal plus work done by spring equals to change in kinetic energy. Work done by gravity will be mgh, work done by normal, the work done by normal of a fixed surface is 0, and the work done by spring is minus k by 2 x square. This has to be equals to the change in kinetic energy. The final kinetic energy is 0, the initial kinetic energy is 0. So what we get is 0 minus 0, which is again 0. Our mission is to find out x. Since we have to find out x, from here we can write mgh equals to kx square by 2, or the maximum compression in the spring equals to under root of 2 mgh by k. So mgh equals to kx square by 2, or x equals to under root of 2 mgh by k. Easy? Let's move on. If a mass m is released from a height h above the spring, write the equation to find maximum compression in spring. If a mass m is released from height h above a spring, write down an equation to determine the maximum compression in the spring. Now here, the common error that students do, they write the equation as mgh equals to half kx square. The initial potential energy stored in the ball because of gravity becomes equals to the final potential energy stored in the spring. Better do not do this. This will give you wrong answer. So sir, what to do? Go strategically, go systematically, go conceptually. So let's see. You will say, assuming maximum compression in the spring to be x. Assume that the maximum compression in the spring is x. At the time of maximum compression of spring, what will be the speed of this mass? 0. It has to be at momentary rest. So you will say, during the journey, two forces are acting on the mass. Which forces? Sir, the force of gravity and the force of spring. So think of the initial case and think of the final case. So initially, the block of mass m or the ball of mass m has been released from a height h, and at the time of maximum compression, let's say the maximum compression is x, the ball is here. At the very initial state, the speed of ball is 0. At the very final state, the speed of ball is 0. So the speed of ball is 0 initially as well as finally. Beta, now we can apply the work energy theorem. We will say from the very initial state to the very final state, the work done by gravity is not mgh, it is mgh plus x, because ball moves total distance down. How much? H plus x. And the work done by spring will be minus kx square by 2. So you will say work done by gravity plus work done by spring equals to change in kinetic energy. Work done by gravity will be mgh plus x. Work done by spring will be minus k by 2 x square, and this has to be equals to the change in kinetic energy. The final kinetic energy is 0, initial 0, so you'll get 0 minus 0. Now solving this particular quadratic equation, you can rearrange it. What you have got is mgh plus mgx minus kx square by 2 equals to 0. You can rearrange this quadratic equation and then you can solve for x. So you will say, on rearrangement, you will get something like this. So solving the quadratic equation, we can find out x. And in the question, you can see, I said, if the mass m is released from height h above the spring, write the equation. I did not ask you for answer, I just want the equation. So I know you guys are smart enough that you will be able to use the quadratic formula minus b plus minus under root of b square minus 4ac upon 2a to reach the answer. But this is how you write the equation. Let's see the next example, and this one is really important. There is a spring of spring constant k and there is a block of mass m. You must remember this particular question. This is super useful question. The question is, if the block is released from the natural length, when the spring is at its natural length, find the maximum elongation in the spring. If the block is released when the spring is at its natural length, determine the maximum elongation in the spring. Now what students do wrong here is that they say that, sir, let's say the maximum elongation is x. So at the time of maximum elongation, the force by the spring should be equal to mg. So the force by the spring kx, if the elongation is x, will be equals to mg, or the maximum elongation has to be mg by k. If you do this, your answer is wrong. Why? Because the correct answer is the maximum elongation is 2 mg by k. And it becomes really easy to understand from SHM. Let's see these three diagrams. The block has been released at its natural length. Moving from the natural length till the mean position. So what is mean position? Where the net force is 0. Where the force of gravity mg becomes equals to the upward force by the spring. So let's say kx, or you will get kx equals to mg, or x equals to mg by k. So here you can see when the elongation is mg by k, the net force on the block will be 0. But moving from natural length till the mean position, the force was always downward. So the block must have gained some speed. If you have done a course on SHM, you will know that going from the natural length till the mean position, the block will attain a speed, and that will be the maximum possible speed of SHM, that will be equals to omega a. So after reaching the mean position, despite the force being 0, the block doesn't stop there. It goes further distance down. How much? The same distance. That's why the final answer comes out to be 2 mg by k. But we will solve this question using work, power and energy. So let's start. At the mean position, net force is 0. Yes, sir. Let's say at the mean position, elongation is x dash. So say elongation is x dash. So you can say that kx dash equals to mg, or x dash equals to mg by k. So at the mean position, the elongation in the spring will be mg by k. Now, on reaching the mean position, block has maximum speed. Hence, the block doesn't stop there. The block goes further down. So, sir, our mission is to find the maximum elongation. How to find it? Very easy. Tell me, at the time of release, what is the speed of the block? 0. At the time of maximum elongation in spring, what will be the speed of the block? 0. So, we can say from the very initial state when released till the very final state when the spring is maximum elongated, the change in kinetic energy is 0. And there are only two forces acting on this block. One, the force of gravity. Second, the force by the spring. So, at the time of maximum elongation, speed is 0. So, from work energy theorem, you can say work done by all equals to change in kinetic energy. And the work done by gravity plus the work done by spring. When the block moves a distance x down, what will be the work done by gravity? mgx. Initially, there is no deformation in the spring. Finally, there is a deformation x in the spring. We know that the work done by spring equals to minus k by 2 into final deformation square minus initial deformation square. That will be equals to minus k by 2 into x square minus 0 square. That will be equals to minus kx square by 2. So work done by all equals to change in kinetic energy. Work done by gravity, mgx. Work done by spring, minus kx square by 2. And this has to be equals to 0. So from here, if we bring this term minus half kx square to the right hand side, we will get that kx square by 2 equals to mg, or x equals to 2 mg by k. So notice that the maximum deformation comes out to be double of the distance traveled till the mean. And isn't it obvious? This is negative extreme. This is mean. This is positive extreme. So if the block moves a distance a from negative extreme to mean, it will further go a distance a from mean to the positive extreme. So if the distance traveled up to mean is a amplitude, the distance traveled from mean to negative extreme will also be a. So the total distance traveled should be double the distance traveled till to reach the mean, right? So I hope you will remember this. This is an important example. Moving on. Let's talk about graphs, and it is really easy. So you know that dw, yes, equals to f dot ds, yes sir. So if I integrate both the side, I will get work done equals to integral F dot ds. What does the area under y-x graph gives you? So the area under y-x graph represents integral y dx. Similarly, we can say that work done equals to integral f dot ds. So the area under the force displacement graph gives the work done. The area under the force displacement graph gives us the work done. So if you ever find a force displacement graph, the area under the graph will be the work done. So easy to remember. Next thing, many a time rather than giving you force displacement graph, they will purposefully gives you acceleration displacement graph. So if they give you acceleration displacement graph rather than force displacement graph, then how to find the work done using the acceleration displacement graph? Sir, the difference between these two graphs is one is force displacement graph, one is acceleration displacement graph. If the area under force displacement graph gives work, and you can say area under force displacement graph is same as area under mass times acceleration into displacement graph. So the area under acceleration displacement graph will give you work done per unit mass. So remember this, if the acceleration displacement graph is given, if we have acceleration displacement graph, its area gives us work done per unit mass. So find the area under the acceleration displacement graph, multiply it with mass, you will get the work done. So the area under acceleration displacement graph gives us the work done per unit mass. Let's continue. There are two types of forces. They are called conservative forces and non-conservative forces. What are conservative forces? Conservative forces are the work done by which in a closed loop is zero. So if you start from a point A, you take up any goddammit path and you come back to the same point A, then beta the work done for a conservative force is zero. So give us some example of conservative force. The force of gravity. If you start from a point A and you come back to the same point A, the work done by force of gravity is zero irrespective of the path chosen. Moreover, electrostatic forces are also conservative in nature. We will talk about this when we learn electrostatic. Right now, remember that there are some forces which are called conservative forces, and conservative forces are the work done by which in a closed loop is zero. There is one more definition of conservative forces, or the work done is path independent. So let's say a particle goes from point A to point B. Irrespective of what is the path chosen, the work done by gravity will be same in all three cases. Example, gravitational forces and electrostatic forces are conservative forces. Moreover, spring forces, which are type of electrodynamic forces, are also conservative in nature. So sir, give us one example of non-conservative force. Remember when I said in the last hour, on a table there is a block and the block is moved from A to B to B to C to C to D, and the block comes back to the same place. Is the work done by friction zero? No. So work done by friction in a closed loop is also not zero. So friction is a classical example of non-conservative forces. So friction force is not a conservative force. Remember this thing. So now let's talk about potential energy. Every time I ask the students, define potential energy. They say, so the energy possessed by a body by the virtue of its position is called potential energy. This definition doesn't help you solve any question. So which definition does? The one I'm going to tell you right now. This will help you in gravitation chapter, electrostatic chapter, in all the other chapters wherever you will listen the term of potential energy. So every time somebody asks you what is potential energy, you will say the change in potential energy equals to minus times the work done by conservative forces. Remember this, the change in potential energy equals to minus times the work done by conservative forces. What are conservative forces? The forces whose work is path independent, the forces whose work done in a closed loop is zero. So the change in potential energy equals to minus times the work done by conservative forces. Okay, so delta U, the change in potential energy, equals to minus times the work done by conservative forces. Just remember this thing. What is change in potential energy? Minus times the work done by conservative forces. Now let's say we have a block of mass m. It is initially on ground and somebody increased its height by h. Question is, what is the change in potential energy of the block? And I know that you know this really well, sir. Change in potential energy of the block will be mgh. But from where do we get this? So we say, as the block goes up, do you know any conservative force that acts on the block? Yes, sir. Which one? The force of gravity. The force of gravity is a conservative force. As the block goes up, the force of gravity mg will be downward. We say that the change in potential energy equals to minus times the work done by conservative force. Here, when the block goes up, what will be the sign of the work done by gravity? So the force is down and the displacement is up. So the sign of work done by gravity will be negative. So you will say the change in potential energy equals to minus times minus mgh. So the change in potential energy is mgh. Just remember, change in potential energy equals to minus times the work done by conservative force. The work done by conservative force in this case is minus mgh. The change in potential energy will be minus times minus mgh. That will be equals to plus mgh. That's why when you raise the block by a height h, the potential energy increases by mgh. Let's see next example. Let's talk about spring potential energy. We know that the change in potential energy equals to minus times the work done by conservative force. As the deformation in the spring changes from, let's say, x1 to x2, as the deformation in the spring changes from x1 to x2, work done by spring equals to minus k by 2 multiplied by final deformation square minus the initial deformation square. Change in potential energy equals to minus times the work done by conservative force. So we will say the change in potential energy equals to minus times the work done by conservative force equals to minus of minus k by 2 into x2 square minus x1 square. So you get the change in potential energy equals to k by 2 times final deformation square minus initial deformation square. So the change in potential energy came out to be same as work done by external agent when the point A moves slowly. Yes. Now let's say if the initial deformation is 0, x1 is 0 and the final deformation is x. So initially the spring is in its natural length and the final deformation, whether compression or elongation, is x. Then the change in potential energy of spring will be k by 2 into final deformation square x square minus 0 square. So you get delta u equals to kx square by 2. So now let's talk about relationship between potential energy and conservative forces. We know that change in potential energy equals to minus times the work done by conservative forces. In the differential format, we can write the infinitely small change in potential energy equals to minus times the infinitely small work done by conservative forces. And we know from the definition of work, dw equals to f dot ds. So we can say the infinitely small change in potential energy equals to minus times the conservative force dot the infinitely small displacement. So this is for 3-dimensional. If we wish to work on 1 dimension, we say that the force in x direction equals to minus del u by del x. The force in y direction equals to minus del u by del y. The conservative force in z direction equals to minus del u by del z. So what is this del? This del is the partial differential operator. When we partially differentiate u, potential energy, with respect to x, we treat y and z as constant. When we partially differentiate with respect to y, we treat x and z as constant. And when we partially differentiate with respect to z, we treat x and y as constant. So the conservative force in x direction equals to minus del u by del x. The conservative force in y direction minus del u by del y. The conservative force in z direction equals to minus del u by del z. Hence, we can combine these three and write the net force equals to minus del u by del x I cap, that is the force in x direction, minus del u by del y j cap, that is the force in y direction, minus del u by del z k cap, that is the force in z direction. When we partially differentiate with respect to one variable, we treat the other variables as constant. What I said, when we partially differentiate with respect to x, we treat y and z as constant. When we partially differentiate with respect to y, we treat x and z as constant. So when we partially differentiate with respect to one variable, we treat the other variables as constant. So let's see an example. Potential energy depends upon coordinates as the potential energy equals to 2xy plus yz square. So if the potential energy depends upon the coordinates as this, question is determine the conservative force at 1, 0, 1. So how to find the conservative force acting when the coordinates are 1, 0, 1. So first of all, from the potential energy and coordinate function, we can find out the conservative force in x direction, the conservative force in y direction, and the conservative force in z direction. We will say the conservative force in x direction equals to minus del u by del x. When you partially differentiate this function with respect to x, you treat y and z as constant. So look at the first part. Differentiation of 2xy. Here you will treat x as variable, while you will treat 2 and y as constant. What do you do to the constant multiplied with variable when you are differentiating? You take the constant out. So you will take 2y outside and the differentiation of x will be 1. Now think of differentiation of yz square. Yz square, we are partially differentiating with respect to x. So we will treat both y as well as z as constant. So there is no x, there is no variable. So the whole function is constant. Since the whole function is constant, its differentiation will be 0. So we will say the force in x direction equals to minus del u by del x equals to minus times the partial differentiation of 2xy plus yz square. 2 and y are treated as constant, take them out, differentiation of x is 1 and the whole of yz square, its differentiation becomes 0. So you get minus 2y. Okay, let's see the next one. What will be the conservative force in y direction? Conservative force in y direction will be minus del u by del y. So you need to partially differentiate this function with respect to y. When you are partially differentiating with respect to y, you will treat x and z as constant. So in the first part, you will say this 2x is like constant and this y is variable. So take the 2x out of the differentiation. Differentiation of y gives you 1. When you differentiate the second part, the differentiation of yz square, you will treat y as variable while you will treat z square as constant. Take the constant out of the differentiation, z square, differentiation of y gives you 1. So you get here simply minus times 2x minus times 2x minus z square. Now the third one, the conservative force in z direction equals to minus del u by del z. This time we are partially differentiating with respect to z, so we will treat x and y as constant. So when I differentiate this first function with respect to z, there is no z. The whole function is a constant and the differentiation of constant becomes 0. When we differentiate the second part, yz square, we will treat z as the variable and y as the constant. So take the constant, which is y, out of the differentiation. Differentiation of z square, beta, will give you 2z. So what you get here is minus 2yz. Now you need to find the magnitude of conservative force at 1, 0, 1. What will be the conservative force in x direction at 1, 0, 1? So the y value is 0. So you'll get minus 2 into 0. That is 0. What will be the conservative force in y direction at 1, 0, 1? So sir, that is minus 2x minus z square. So that will be minus 2 into 1 minus of z square. That is again 1 square. So that comes out to be minus 3. What will be the conservative force in the z direction? Minus 2xy. Since y coordinate is 0, you will get minus 2 into 0 into 1. That comes out to be 0. Hence we can say at 1, 0, 1, the force in x direction 0. The force in y direction minus 3. The force in z direction 0. Hence the net force will be reported as 0 I cap minus 3 j cap plus 0 k cap. So that is nothing but minus 3 j cap. So this is one example based on how to find the conservative forces based on the potential and position function. We will practice more these type of questions. I will teach you relationship between potential and field. So let's continue. So now let's talk about the type of equilibriums. There are 3 types of equilibrium: stable equilibrium, unstable equilibrium, and neutral equilibrium. But what exactly is equilibrium? Equilibrium is the state where the net force is 0. So we have classified 3 types of equilibrium. First, let's talk about stable equilibrium. If displaced from equilibrium position, the body tries to re-attain the original equilibrium position. It is called stable equilibrium. So when you displace the body from the equilibrium position, but the body tries to re-attain the original equilibrium position, that is called stable equilibrium. For example, if you put a small pebble in a bowl, if you displace the pebble a little bit towards right and release it, it tries to go back to the original equilibrium position. Or if you displace it towards left and then you release it, it again tries to go back to the original equilibrium position. There is one thing that can be said about stable equilibrium. Let's say there is a particle, and at a place I am saying here is the position of stable equilibrium. This means that if I will displace the particle from here a little bit towards right, what will be the direction of the force on this particle? So stable equilibrium is the type of equilibrium where the particle tries to re-attain its equilibrium position. So sir, if you displace this particle from here a little bit towards right and it tries to re-attain the original equilibrium position, then the force on the particle has to be towards left. And if you displace from the equilibrium position a little bit towards left, and I am telling you that this is a stable equilibrium position, then you will say, sir, on displacing little bit towards left, the particle will try to re-attain the original equilibrium position. Hence, the force on the particle will be towards right. So, we can say, if you have got stable equilibrium, then displacing a particle to the right of equilibrium, it experiences a force towards left. And when you displace the particle to the left of equilibrium, it experiences a force towards right. And this is easy to remember keeping in mind this bowl and pebble example. When we move the pebble little bit towards the right, the force is backwards, trying to bring it back to the original equilibrium position. And when we displace it little bit towards the left, it has a net force towards right, trying to bring it back towards right. So when displaced from equilibrium position, if the particle try to re-attain the original equilibrium position, that is the case of stable equilibrium. So now let's talk about the next type of equilibrium, unstable equilibrium. If displaced from the equilibrium position, the body keeps on moving away from the equilibrium position. It means that when displaced from the equilibrium position, the body does not come back towards the equilibrium position. To the contrary, it keeps on moving away from the equilibrium position. That is the example of unstable equilibrium. The classical example is an upside down bowl, and on the top of bowl you place a pebble. So if you have placed the same bowl upside down and then on the top you have somehow managed to place a pebble. Now if you displace the pebble a little bit towards right and release it here, you know that this pebble is not coming back. This pebble will keep on moving forward. This means that when you displace it little bit towards right, it has a net force towards right. And if I displace this pebble from the equilibrium position little bit towards left and release it here, then it keeps on moving towards the left because it has a force towards left. So when on displacing from the equilibrium position, the particle do not move towards the original equilibrium position. To the contrary, it moves away from the equilibrium position. We say this type of equilibrium is unstable equilibrium. So if this is the equilibrium position, you shift the particle a little bit towards the right and the force is towards right. That is unstable equilibrium. If you shift it a little bit towards left and the force is towards left, you call it unstable equilibrium. So the third type of equilibrium we talk about is neutral equilibrium. When the body neither tries to re-attain original equilibrium nor move away from it. When the body doesn't care. Okay, so let's say you have got this pebble on a flat surface. I move this pebble a little bit towards right and release it here. Will it try to go back to the original equilibrium position, or will it try to move away from the original equilibrium position? No. This type of equilibrium is called neutral equilibrium. When it doesn't matter, you displace it a little bit towards right or a little bit towards left, wherever you place it, it stays there. It does not try to re-attain the original equilibrium position, nor does it try to move away from it. So here, in the case of neutral equilibrium, if you have an equilibrium position, you displace it a little bit towards right, there is no force. You displace it a little bit towards left, there is no force. Moving on. The graph shows potential energy versus position graph. Determine the direction of conservative force at x equals to x1 and x equals to x2. So this graph is the potential versus the position graph. You have to tell what is the direction of force at x equals to x1 and at x equals to x2. You will say, we know that the force in x direction equals to minus del u by del x. So the force in x direction is nothing but minus types of slope of ux graph. Now we can say force conservative equals to minus del u by del x. At x equals to x1, the slope is positive. If you draw a tangent here, at x equals to x1, the slope is positive. If at x equals to x1, the slope of ux graph is positive, what will you say about fx? Fx is minus times the slope of ux graph. If at x equals to x1, the slope is positive, then the force will be negative. There is a minus sign, right? So, hence the force is negative. And at x equals to x2, if you draw a tangent here, the angle made by this tangent with the positive x-axis will be obtuse. So you will say that the slope of this graph is negative. If the slope of the graph is negative, then from force equals to minus del u by del x, you will say if the slope is negative, you will get the force to be positive. So at x equals to x1, the force is towards negative direction. At x equals to x2, the force is towards positive direction. Now simple question, at this peak point, let's call it x dash. What will be the direction of force? At the peak point, what will be the direction of force? Yes. Sir, if you draw a tangent at the peak point, now, the slope of this tangent is 0. If the slope of the tangent is 0, and we know that force equals to minus del u by del x. So where the slope becomes 0, the force becomes 0. And where the force becomes 0, we say that that is the position of equilibrium. So we can say, if we think of the position of the peak, let's call it x dash. Then at x dash, since the slope of ux graph is 0, we can say that at x dash, the force is 0, and hence this is the point of equilibrium. Now the big question comes, this is the point of stable equilibrium or unstable equilibrium. So let's talk about it in the next question. Mark the position of equilibrium and determine the type of equilibrium. So in this graph, there is potential energy versus position graph, and on the graph you have got multiple points x1, x2, x3, x4, x5, x6, x7. Question is, out of all these points, which points are position of equilibrium and what is the type of equilibrium? So you will say, for equilibrium, the force has to be 0. And from F equals to minus del u by del x, beta, if the force has to be 0, it means that del u by del x has to be 0. Del u by del x is 0, it means that the slope of potential position graph has to be 0. The slope of potential position graph has to be 0. Where on this curve, the slope is 0. So sir, at x equals to x1, at x equals to x4, and at x equals to x6. If you draw tangent at these 3 points, then for these 3 points, the slope is 0. So we can say, for equilibrium, forces has to be 0. So del u by del x has to be equals to 0. Hence, the slope of the potential energy versus the position graph has to be 0. Now, at x equals to x2, x4 and x6, x2, x4 and x6, we have got the slope, that is del u by del x equals to 0, hence the force equals to 0. So these are the position of equilibrium. Now comes the big question, which type of equilibrium is this? Is stable, unstable or neutral? So we can identify the type of equilibrium using a basic rule. X equals to x2 is the point of equilibrium. Yes. Think of a point just before x2. Okay. At this point, the slope of the ux graph is positive. If the slope of the ux graph is positive, then the force has to be negative. Think of a point just after x equals to x2, somewhere here. At this point, the slope of the graph is negative. Hence, the force has to be positive. So think of the points around x2. So at a point on the left of x2, the force is negative. At a point on the right of x2, force is positive. So if I have a particle at x2, I displace it little bit towards right, then the force is towards right. When I displace it little bit towards left, the force is towards left. This is the classical example of unstable equilibrium. So at x equals to x2, we get unstable equilibrium. What about x equals to x4? You will say, so just before x4, at x4, the slope is 0, so the force is 0, hence it is the position of equilibrium. Just before x4, if you draw the tangent on the curve, it makes obtuse angle. Hence the slope is negative, hence the force is positive. And just after x4, if you think of the tangent at this point on curve, the slope is positive, hence the force has to be negative. So just look at this much part and focus. At a point to the left of x4, the force is positive. At a point to the right of x4, the force is towards left. So when I displace a particle from x4 towards right, the force is towards left. When I displace a particle from x4 towards left, the force is towards right. Which type of equilibrium is this? A stable equilibrium. So x4 is the point of stable equilibrium. And I have got an even easier solution. The universe craves for stability, and stability is attained at lower energy levels. So at x equals to x2, as the potential energy is highest, it is unstable. It is unstable. The universe craves for stability, and stability is attained at lower energy level. At x equals to x4, we get minimum of energy. Hence, at x equals to x4, the equilibrium is stable. So we will say x2, x4, x6, x2, x4, x6, all three are position of equilibrium, out of which x2 and x6, where the energy is higher, are unstable equilibrium, and x4, where the energy is least, is the position of stable equilibrium. So x2 and x6 are position of unstable equilibrium, while x4 is the position of stable equilibrium. Easy? Let's move on. So mechanical energy conservation. We know that the sum of kinetic energy and potential energy is called mechanical energy. The sum of kinetic energy and potential energy is called mechanical energy. But I am not teaching you what is mechanical energy. I am teaching you what is mechanical energy conservation and under which condition you can do mechanical energy conservation. From the work energy theorem, we know that work done by all the forces equals to change in kinetic energy. Quite simple. Now think of system of particle. What type of forces can act on it? There might be some external forces, or there might be some internal forces. The internal forces can be of two types. They can be conservative or they can be non-conservative. For example, if I take a vessel, fill it up with water and then place a ball in it. If I shake the bottle, the ball will move up and down and the water will apply viscous force on it. This type of force will be non-conservative internal force for the whole bottle system. Okay, so from the work energy theorem, we know that work done by all the forces equals to change in kinetic energy. So we can say work done by external force plus work done by internal conservative forces plus the work done by internal non-conservative forces equals to change in kinetic energy. I want you to visualize that I bring this term, the work done by internal conservative forces, to the right. So we can say work done by external forces plus the work done by internal non-conservative forces, maybe viscous force or friction force, equals to change in kinetic energy minus the work done by internal conservative forces. What is minus times the work done by conservative forces? So minus times the work done by conservative forces is change in potential energy. So we can say the work done by external forces plus the work done by internal non-conservative forces equals to change in kinetic energy plus change in potential energy. The work done by external forces plus the work done by internal non-conservative forces equals to change in kinetic energy plus change in potential energy. Now think of one case. What if no work is being done by external forces? If no work will be done by external forces, then this first term will become 0. As well as if, let's say, internal non-conservative forces are absent, there is no viscous force, there is no friction force, so and the internal non-conservative forces are absent, then the work done by internal non-conservative forces will also be 0. So you can say, if the work done by external forces is 0 as well as the work done by internal non-conservative forces is 0, then the change in kinetic energy plus change in potential energy will be equals to 0. And this particular statement is called mechanical energy conservation. Just the way knowing momentum conservation and knowing the condition when you can apply momentum conservation, both are equally important. In the same way, knowing mechanical energy conservation, that change in kinetic energy plus change in potential energy equals to 0, as well as under which condition you can apply it, knowing both of them are equally important. So you can do mechanical energy conservation when the work done by external forces is 0 as well as there is no internal non-conservative force present. So let's see one example. Can internal forces change kinetic energy and momentum of the system? Can internal forces change kinetic energy and momentum of the system? So if you have system of particle, can the internal forces applied by them on one another, can that change the kinetic energy or can that change the momentum? So let's see. Let's first of all talk about momentum. If we have two masses released in space, visualize just two masses released in space, and they are moving towards each other under the influence of force of gravity, the force applied by them on each other will be equal and opposite. So they apply gravitational force of attraction on each other of same magnitude but in opposite direction. As the force act for same time and have opposite direction, both of them develop momentum of same magnitude but in opposite direction. So the momentum transferred to both the masses are equal and opposite. Momentum is a vector quantity. If the first mass develops a momentum p towards right and second a momentum p towards left, the net momentum of the system remains unchanged. So remember that internal forces can't change momentum of a system. That's why when we do momentum conservation, we say that the net external forces should be 0 because internal forces can't change the momentum. Hence, no change in momentum of system. What about the kinetic energy? Now just visualize these two masses. If on the first mass the force is towards right, eventually it will displace towards right. What will be the sign of the work done by the force of gravity on this first mass? So sir, force is towards right, it will displace towards right, so the work done will be positive, so its kinetic energy will increase. Now forget the first mass, think of the second mass. On the second mass m2, the force is towards left, because of which it will accelerate towards left, it will gain some velocity towards left, and eventually it will displace towards left. On the second mass, the force and displacement are again in the same direction. So on the second mass also, you will say that the work done is positive and its kinetic energy will also increase. So as both the masses move closer, internal force is doing positive work on both of them. Internal forces can change the kinetic energy of the system. So we will say, but as the masses move closer, work done on both the masses is positive. By the force of gravity, work done on both the masses is positive. Hence, energy of the system increases. So, not energy, not the right word. Hence, kinetic energy. Okay. Hence, kinetic energy of the system increases. So, internal forces can change the kinetic energy of the system, but internal forces can't change the momentum of the system. So, now let's do one question, which is important. In the question, we are given two blocks, one of mass m, one of mass 2m. The block of mass 2m has been given a speed u, and the block of mass m is at rest. And there is a spring placed between them, which is right now at its natural length. Now, as you can see, the block on the left has been given some velocity, while the block on the right is at rest. So the spring will get compressed. Your mission is to find the maximum compression in the spring. So how to do these type of questions? There is one really important statement to solve these type of question. And first of all, let's understand that statement. Let's say there are two friends, 1 and 2 on a road. And let's say their position is given by x equals to x1 and x equals to x2. If I ask you what is the position of 2 with respect to 1, you will say that's our position of 2 with respect to 1 equals to x2 minus x1. And that will be represented by this vector, position of 2 with respect to 1. I ask you, when will this x21 be maximum or minimum? So you will say, if the position of 2 with respect to 1 changes with time, whenever x21 will be maximum or minimum, x21 by dt will be 0. The rate of change of their separation with respect to time will be 0. If y is a function of x, whenever y is maximum or minimum, dy by dx is 0. So if the position of 2 with respect to 1 changes with time, whenever it will be maximum or minimum, dx21 upon dt has to be 0. When I say that dx21 upon dt has to be 0, it means that the velocity of 2 with respect to 1 has to be 0. It means that velocity of 2 minus velocity of 1 has to be 0. It means that velocity of 2 has to be equal to velocity of 1. So whenever the separation between these two people will be maximum or minimum, they are bound to have the same velocity along the line joining them. And this is the statement that we are going to use to find the maximum compression in the spring. Whenever the compression in this spring will be maximum, the block of mass 2m and m will be closest. So when the separation between them will be minimum, they both should have the same velocity. So at the time of maximum compression, both the blocks will have same velocity, and here we have assumed that velocity to be v. Now how can we find v, this common velocity, at the time of maximum compression? From the momentum conservation, we can say there is no external force acting on the system. So from momentum conservation, we will say the initial momentum of system, initially only the block of mass 2m has momentum, 2m into u, and the block of mass m does not have any momentum, has to be equals to final momentum. The final momentum will be 2mv plus mv. So from here we can see that 2mu equals to 3mv, or v equals to 2u by 3. So the final common velocity with which both the blocks will move is 2/3 of the initial velocity of the block of mass 2m. But sir, our mission is not to find the common velocity at the time of maximum compression, which is 2u by 3. Our mission is to find the maximum compression. Now to find the maximum compression, we will use the mechanical energy conservation. The mechanical energy conservation says that initial mechanical energy of system has to be equals to final mechanical energy of the system. Initial mechanical energy is nothing but initial kinetic energy plus initial potential energy. Final mechanical energy has to be final kinetic energy plus final potential energy. So, using the mechanical energy conservation, we can say initial kinetic energy plus initial potential energy equals to final kinetic energy plus final potential energy. Initial kinetic energy of this system will be how much? That initially the mass 2m has a speed u, yes, and the second mass has got 0 speed. So all the kinetic energy of the system is just with the first mass. So the initial kinetic energy of system will be half into 2m into u square. What will be the initial spring potential energy? So since initially the spring is at its natural length, the initial spring potential energy will be 0. So we can write the initial kinetic energy plus the initial spring potential energy. And this has to be equal to the final kinetic energy plus the final spring potential energy. The final kinetic energy will be half into 2m into v square plus half into m into v square. If you take half v square common, you will be left with half v square times 2m plus m, that becomes 3m. So you can write half into 3m into v square. In place of V, you can write 2U by 3. So you can write the final kinetic energy of the whole system of both the blocks combined to be equals to half into 3m into 2u by 3 whole square. And let's say the deformation in this spring comes out to be x. So you will write the final spring potential energy as half kx square. So initial kinetic energy plus initial potential energy equals to final kinetic energy plus final spring potential energy, which is half kx square. Once you have made this equation, bringing this whole term to the left hand side and solving, you can find out the value of x, which is the maximum compression. And on solving this, you get x equals to under root of 2mu square by 3k. To understand the concept better, let's practice one more question based on this. Now let's say the initial condition is such that the block of mass 2m has a speed 2u towards right, while the block of mass m has a speed u towards left, and initially the spring is at its natural length. Question is, if initially the spring is in natural length, find the maximum compression in the spring. Again, we will use the same statement. At the time of maximum elongation or at the time of maximum compression in the spring, both the blocks must have same velocity, same magnitude, same direction. Let's say we call it V. We can find out V using the momentum conservation. We can say that since no external force is acting on the system, the initial momentum of the system has to be equal to final momentum of the system. So from momentum conservation, initial momentum of the system 2m into 2u minus m into u. This has been taken as negative because momentum is a vector quantity. The second mass has got momentum towards left. So the net initial momentum towards right, 2m into 2u minus m into u, has to be equal to final momentum of the system, which is 2m into v plus m into v. So that becomes 3mv. So on the left hand side, you get 4mu minus mu equals to 3mv, or 3mu equals to 3mv, or cancelling out 3 and 3m, you get u equals to v. So the final common velocity comes out to be equals to u. But our mission is to find the maximum compression. To find the maximum compression, now we will do mechanical energy conservation. That is initial kinetic energy of system plus initial spring potential energy of system equals to final kinetic energy of system plus final spring potential energy of system. Initial kinetic energy of system will be equals to half into 2m into 2u square, kinetic energy of first block, plus half into m into u square, the kinetic energy of second block, plus the initial spring potential energy. Since initially the spring is at its natural length, the initial spring potential energy is going to be 0. And this has to be equal to the final kinetic energy of system plus final spring potential energy of system. The final kinetic energy of system will be half into 2m into v square plus half into m into v square. That becomes half into 3m into v square. Take half v square common, you get 2m plus m, that becomes 3m. And we know that v is equals to u. So the final common kinetic energy of system becomes half into 3m into u square plus the spring potential energy. Let's say the final compression is x. So the spring potential energy is half kx square. Again, bringing this term to the left hand side and solving, you will get x to be equals to under root of 6mu square by k. Try it out. So if you find more questions of this type and you are not able to answer, put them on the Telegram discussion group and I will post the solution. Let's move on. If the position of a particle of mass 2 kg changes with time as x equals to 4t square plus 6t plus 2, determine the work done on particle from time equals to 0 till time equals to 1 second. So they have given you position as a function of time and you have to find the work done on the particle within a certain time frame. Now when students see this question, they say, okay, position is given as function of time. If I differentiate it one, I will get velocity as a function of time. And if I differentiate it again with respect to time, I will get acceleration as a function of time. Then if I multiply with the mass, I will get force as a function of time. Then I will multiply this force with dx and then I will integrate f dx to get the work done. Don't do this. This is really long method. Then sir, what to do? use the work energy theorem. Work done by all the forces equals to change in kinetic energy. If you need to find the work done on the body, it's better to find the change in its kinetic energy. To find the change in kinetic energy, you just need two things, the final kinetic energy and the initial kinetic energy. To find the final kinetic energy, you need the final speed. To find the initial kinetic energy, what you need is the initial speed. So focus on finding the initial speed to find the initial kinetic energy and the final speed to find the final kinetic energy, so that subtracting them, you can get the work done. So you will say as x equals to 4t square plus 6t plus 2. We can say that differentiating v comes out to be equals to dx by dt, and the differentiation of 4t square plus 6t plus 2 with respect to time will give you 8t plus 6. Differentiated, you will get 8t plus 6. Now you know velocity or speed at any time. If you know speed at any time, you definitely know speed at time equals to 0 and at time equals to 1. So at time equals to 0, substituting t equals to 0, you get v equals to 8 into 0 plus 6, that becomes 6. At time equals to 1, you will get speed equals to 8 into 1 plus 6, and 8 into 1, 8 plus 6 gives you 40. So the work done has to be equals to change in kinetic energy. The change in kinetic energy can be written as half m into v final square minus v initial square, and just plug in the value of final speed as 14 and initial speed as 6. So you get half into mass 2 into 14 square minus 6 square. 2 and 2 get cancelled. 14 square minus 6 square gives you 160. So what I told you here is, whenever you get a question in which some function is given and you need to find the work done, try to find the initial and final kinetic energy. So let's practice one more question of the same time. If the speed of a particle of mass 2 kg depends upon position as v equals to 4x square plus 2, determine the work done by force on the particle move from x equals to 0 to x equals to 1. So when the particle goes from x equals to 0 to x equals to 1, what is the work done by the force on the particle? So here again, you have speed as a function of position. Yes, sir. And you need to find work done from x equals to 0 to x equals to 1. So you will say at x equals to 0, the speed will be how much? 4 into 0 square plus 2. And 4 into 0 square plus 2 is 2. So the speed will be 2. At x equals to 1, the speed will be equals to 4 into 1 square plus 2. 4 into 1 square becomes 4. 4 plus 2 gives you 6. So the speed is 6. Now once you know that what is the speed at x equals to 0 and what is the speed at x equals to 1, using these initial and final speed, you can find the initial and final kinetic energy. And once you know both the kinetic energy, subtracting them, you can find the work done. So you can say work done is simply equals to change in kinetic energy equals to half into m into v final square minus v initial square. Substitute m as 2, v final as 6 and v initial as 2. So you get half into 2 into 6 square minus 2 square, cancel out 2 and 2. 6 square minus 2 square gives you 36 minus 4, that is 32 joule. Simple. Now let's understand the concept of power. Power is nothing but the rate of doing work. Power is nothing but the rate of doing work. Mathematically, we say that power equals to dw by dt. Now whenever I write this type of equation, power equals to dw by dt or velocity equals to dx by dt, every time I say two things. When I write v equals to dx by dt, I say the slope of xt graph gives you velocity and the area under vt graph gives you the displacement. The same thing I will say here. The slope of work time graph gives you the power. How much work has been done in how much time. The slope of work versus time graph gives you the power delivered. And the area under power and time graph gives you the total work done. The area under power time graph gives you the total work done. This is something you should know. Just like after defining instantaneous velocity as dx by dt, we say that the average velocity is total change in position upon total time taken. Similarly, once we know that instantaneous power is dw by dt, we can also say average power delivered equals to total work done upon total time taken. What is total work done? The work done by all the forces equals to change in kinetic energy. So in place of total work done, we can even write the change in kinetic energy upon time taken. So we can write the average power delivered as the change in kinetic energy upon the time taken. The change in kinetic energy upon the time taken. This is the average power delivered. Now, we know that the instantaneous power is given by dw by dt, and the first thing I taught you in work power energy was that dw equals to f dot ds. So if in place of dw I write f dot ds, taking this ds by dt, you can write ds by dt is the rate of change of position with respect to time. So this becomes f dot v. So power can be taken as the dot product of force and velocity. So we can say power equals to f dot v equals to magnitude of force into magnitude of velocity into cos of the angle between them. Now the sign of power will depend upon the angle theta. If the theta is acute less than 90 degree, then cos theta will be positive and hence the power delivered to the particle will be positive, and if the power delivered to the particle is positive, the kinetic energy will increase. If the angle between force and velocity is 90 degree, then the power delivered will be 0 because cos 90 is 0. And when the power delivered is 0, the kinetic energy remains constant, neither increases nor decreases. The second case is really important for magnetism because the magnetic force acting on a charged particle is in the direction perpendicular to its velocity. So for theta equals to 90 degree, power delivered is 0, hence the kinetic energy remains constant. Now the last case, if the angle between force and velocity is obtuse, theta is greater than 90 degree, then the power delivered will be negative. If the power delivered is negative, then we can say that the kinetic energy will decrease. So now let's do two important problems based on power. The first one, if a constant power is supplied to a particle at rest, its velocity at any time t is given by v proportional to t raised to the power of n, find n. So this is the first question. So as per the problem statement, the power delivered is constant and initially the particle is at rest. So we can say power is constant. Let's call it K. Since we know that power is force dot velocity, so we can say that Fv has to be equals to constant. We know that force equals to mass into acceleration, and mass into acceleration can be written as m into dv by dt. So this force times velocity can be written as m into dv by dt times v, and this has to be equals to K. Now we can do some rearrangement. We can keep v dv on one side, bring this dt up and this m down. So we can write v dv equals to K by m times dt. Integrating both the sides, we can say integration of v dv will give us v square by 2. And K by m is constant, take it outside. Integration of dt gives you t. Now you can bring the 2 up and take the under root, game over. So we can say that v equals to under root of 2kt by m, hence v proportional to root t, or we can say v proportional to t raised to the power of half, hence bachon n has to be nothing but half. So this is a simple yet important question. So if a constant power is supplied, then the velocity is proportional to t raised to the power of half. Now let's see the next important question that gets asked. If a motor takes water from rest and provide it speed v, what is the power of the motor? So let's say this is our motor. The motor takes water from a tank where the water is at rest, and the motor provides it a speed v. What will be the power of this motor? So in the chapter of forces, we have learned that the force required to move this water with a speed v is nothing but rho av square, where rho is the density of fluid, a is the cross-sectional area, and v is the speed with which the fluid comes out. If the force equals to rho av square, then what has to be the power? Power has to be force times velocity, as the force and velocity will be in same direction. So we can say that power is nothing but force rho av square times v. So the power comes out to be rho av cube. Why this particular example is important? You should know that the power is proportional to v cube. the power is proportional to VQ. So they will ask you questions like, if the flow rate is doubled, what happens to the power? As power is proportional to VQ, when the flow rate is doubled, the power becomes 8 times. So P proportional to VQ. Or the counter question of this thing is made, if you have a windmill and one day the wind is going with speed V. On another day, when the wind speed is 2V, how many times power will be produced? So when the speed of the wind becomes double, the power produced by windmill becomes 8 times. So remember that P proportional to VQ for both motor as well as windmill. So that's all in work power energy. See you guys in the next hour. Bye bye. So that's all for now. See you guys in the next hour.